Hello, this is Mason Haggerty with question 5.81 from the Fundamentals of Heat and Mass Transfer, 8th edition from Bergman. This question asks us to consider the plane wall of thickness 2L, the infinite cylinder of radius RO, and the sphere of radius RO. Each configuration is subjected to a constant surface heat of Qs. Using the approximate solutions of table 5.2b for Fourier number is greater than or equal to 0.2, derive expressions for each of the three geometries for the quantity of Ts actual minus Ti all over Ts lumped capacitance minus Ti. In this expression, Ts actual is the actual surface temperature as determined by the relations of table 5.2b, and TSLC is the temperature associated with lumped capacitance behavior. Determine criteria associated with Ts actual minus Ti over TSLC minus Ti, which is equal to or less than 1.1, that is, determine when the lumped capacitance approximation is accurate to within 10%. So here I just pulled out the information from the question just for reference while working through the problem, but it's just everything that the question has said. Over here I've included excerpts from the table that was referenced in the question. So as we can see, for the three different cases we're given the approximate solutions given that the Fourier number is less than 0.2 or greater than or equal to 0.2. For this question we only care about the approximate solutions for Fourier number greater than or equal to 0.2. I've also added in the characteristic length for each scenario, just again for quick reference. Below the table here, I've written some definitions. So Q star is defined as Qs times the characteristic length over K times the surface temperature minus the initial temperature. The Fourier number is defined as alpha T over LC squared. I don't have it written here, but alpha is also defined as K over rho C, or in this case Cp, and then we have Ti equals the initial temp. So using those definitions and kind of looking at the table, we can see that generally for all the cases you get the equation Qs times Lc over K times Ts actual minus Ti is equal to A, so just a constant, times Kt over rho C Lc, or Lc squared plus B, again another constant, all to the negative 1. So again, that's kind of up to the table there. You can see that it's basically a constant multiplied by the Fourier number plus a constant, all to the negative 1. And we define that as equation 1. So next, for lumped capacitance with constant heat flux, we know that Qs times the surface area times time equals rho C times the volume times TSLC, lumped capacitance, minus Ti. So rearranging this, you get TSLC minus Ti equals, and here we sub in the surface area and volume to get A, which is actually the same A as before from the previous equation, times Qs times T over rho C times the characteristic length. This gives us equation 2. So next, we solve equation 1 for the Ts actual minus Ti, and you're going to divide that by equation 2. And so this gives us Ts actual minus Ti over Ts lumped capacitance minus Ti is equal to Qs times the characteristic length over K, all times A, again that constant, times K over rho C times T over Lc squared plus B, again the other constant, and then multiply that by rho C Lc over A Qs times T. Simplify this out, you get 1 over A times the Fourier number times A times the Fourier number plus B, which again, simplify that out, multiply it through, you get 1 plus B over A times the inverse of the Fourier number. This is the general equation that we're going to be using for the rest of the question. And basically we're just going to plug in each of the cases by pulling the A and B out of the table given a solution and solving for each case. So first, for the plane wall, again, remember that Fourier number, the solution is Fourier number plus 1 over 3 inversed. And so from that, you can see that A equals 1 and B equals 1/3. And so you're going to get that Ts actual minus Ti over Ts lumped capacitance minus Ti is equal to 1 plus B over A times the inverse of the Fourier number, which just equals 1 plus 1/3 inverse of Fourier number. For the infinite cylinder, we know that it's 2 Fourier number plus 1/4 inverse, so you have A equals 2 and B equals 1/4. So this gives you that Ts actual minus Ti over Ts lumped capacitance minus Ti is equal to 1 plus B over A times the inverse of the Fourier number, which equals 1 plus 1 over 8 times the inverse of the Fourier number. Finally, we have the sphere, where it is 3 times the Fourier number plus 1 over 5 inversed, so A equals 3 and B equals 1/5. So this gives you Ts actual minus Ti over Ts LC minus Ti is equal to 1 plus B over A, Fourier number inversed, which equals 1 plus 1 over 15 times the inverse of the Fourier number. So remember, this question is asking us to determine the criteria associated with Ts actual minus Ti over Ts LC, lumped capacitance, minus Ti, when that is less than or equal to 1.1. So then again is to find when the lumped capacitance approximation is accurate to within 10%. So to do that, we set these equations that we just solved to 1.1, and we solve for the Fourier number in each case. And so for the plane wall, we get Fourier number critical, that's the FOC, is equal to 3.33. For the infinite cylinder, it is 1.25, and for the sphere, it is 0.667. So for this case, we know that LC behavior is exhibited at dimensionless times greater than FOC. And also, we can just do a quick check and see that because all of our FOCs are greater than 0.2, that our use of the Fourier number greater than or equal to 0.2 for the approximate solution was the correct choice. And yeah, that's it for this question. Thank you.